Welcome back. We have been discussing on AFM imaging, atomic force microscope imaging. We have three different modes of operation, contact mode, non-contact mode and intermittent or tapping mode of measurements. And contact mode is called static mode, and non-contact and intermittent contact or tapping mode are the dynamic mode of AFM operation. Today we will see how the dynamic mode of AFM operation produce another type of image in the atomic force microscope, that is called phase image. In addition to that, we will discuss about the noise and resolution in atomic force microscope. So, this is what we will discuss in this lecture. Let us first go to phase imaging. I have briefly told you that when the probe or cantilever oscillate above the surface of a sample, not only we measure how the amplitude changes, but also we can measure the phase shift of those oscillation. By measuring the phase shifts of those oscillation, we can know whether there is a different kind of sample on the surface or it is all everywhere uniform. So, the phase from those phase shift value, we can create an image of different contrast. So, the phase shift produce a phase image that you will see here. The phase contrast can be again varied by changing the amplitude of the oscillation. So, one of the oscillation that we drive at one particular oscillation, amplitude of the oscillation, that is called set point value. So, for example, this is a particular oscillation value at which that let us say this blue color or not, let us say this dash line, the oscillation is happening with a particular amplitude. That amplitude we can change as per our requirement, and that can be changed by choosing suitable type of cantilever with a different value of spring constant. So, when a cantilever oscillates at its resonance frequency, that is we say pre cantilever oscillation, or that amplitude we can say pre cantilever oscillation amplitude A0. Now, we can change this to a particular that oscillation we can drive to a different set point value. So, if we change the set point value, that is that oscillation, that amplitude is called ASP, and that ratio we can vary. That ratio is termed as RSP, ratio of set point value amplitude to the free oscillation amplitude. RSP is equal to ASP, set point oscillation amplitude divided by the free cantilever oscillation amplitude. By changing this RSP value, phase contrast can be also changed, that you will see. And this phase constant phase shift is depends on the quality factor of the cantilever, spring constant. We can write the phase shift del phi 0 is equal to pi by 2 minus tan inverse spring constant divided by quality factor into sigma. So, this sigma is the change in the force gradient or derivative of the force gradient del F by del Z. F is the interaction force between the sample and tip, and Z is the tip sample gap, distance between tip and sample, distance between tip and sample, sigma, and Q is the quality factor. Q is the quality factor, and K is the spring constant. spring constant value. So, this is the phase shift occurs and the it can be simplified to a equation like we can write del phi 0 is almost equal to q sigma divided by k. Here this force gradient or sigma value supposed to be less than the spring constant of the cantilever k value. So, the phase shift normally phase shift occurs in the range of 0 to phase shifts occur from 0 to 180 degree, and if the phase shift value is between from minus 90 degree to 0, that is if it is a negative value, phase shift is occurring in the negative direction, then this is due to the attractive force. This is due to the attractive force, and the attractive force, our force gradient is also negative. And if the phase shift is occurring from 0 degree to plus 90 degree, then it is due to repulsive force. So, by knowing that which direction phase shift is occurring, we can know whether it is due to attractive force or whether it is due to the repulsive force. So, this phase shift from the original drive signal to the detector signal can tell us how much phase shifts and in which direction, and that code gives us the phase image that you will see here in some examples. Here is an example of a polymer blend. This polymer blends have two components. So, those components are one is polyethylene co-styrene, another is polydimethyl phenylene oxide. There is two components polymer, and these two component polymers, this is a polymer blends. There are two components, and if we look at the topography and phase image in the in the left side, this is topography image and right side is a phase image. Topography image do not show any difference in the contrast, almost it is uniform. We cannot differentiate there are two different phases are well separated or not. But in the phase image we can see there are darker portion and other portion. These are some darker portion and there are other brighter portion. So, which are due to two different materials in the sample, and thereby their phase value are different, phase shift value are different. So, this is done when a RSP value was RSP value was 0.8. RSP value 0.8 means it is a light tapping. Light tapping means there is very the tapping, light tapping. This is in tapping mode. The measurement is in the tapping mode, left side topography, because all the time this phase imaging can only be obtained in the tapping mode or in non-contact mode when the tip oscillate. Light tapping means the set point value is close to the free cantilever oscillation amplitude value. So, these two value are when they are close, that then RSP value is high, then we can say light tapping. So, in the light tapping also, at the light tapping we could see the difference in contrast in phase imaging, but not in the topography image. But if we increase the tapping force by reducing the amplitude, so as you can see in that it is a medium tapping, then when RSP value is very low, it is normally less than 0.4. This light tapping is almost like greater than 0.8. On the other hand, medium tapping is normally 0.4 to 0.8, and if it is less than, it is hard tapping. It is less than 0.4. So, at hard tapping and medium tapping, in these two cases we can see both the topography and the phase image showing distinct two phases, no problem. In both cases we can medium tapping and hard tapping, both cases we could see there is a different contrast at different region, indicating there is a two component system. Now, this contrast variation is in the 5 nanometer range, like The darkest part and brightest parts are 5 nanometer difference. Phase angle variation with is 5 degree in A, 5 degree in A. That means, in the light tapping we have only small phase angle change with a phase angle variation is 5 degree in A, and B A and B, and but 30 degree in the range C. Here phase angle this phase angle variation, phase contrast variation, the darkest and the brightest angle variation, phase angle variation or phase shift value variation is much higher, 30 degree. That is why we see much brighter and much darker contrast in the hard tapping, but image size is 1.8 to 1.8 micrometer. But important point here not to that, here also we could get some indication about the two phase separation when where medium tapping and hard tapping, but it is this is a polymer sample. Medium tapping and hard tapping could deform and distort the sample. Therefore, a hard tapping or medium tapping is not preferred. We have to do a light tapping, so that we will not damage the surface. Even though we do tapping modes and damage possibility is low, but still if we do hard tapping, still we could damage the sample surface. Therefore, without damaging the sample surface, with a light tapping we could get the phase separation in the phase image by doing light tapping. That is the important of phase image in determining the inhomogeneity in the sample quite distinctly. Taken another example, that was a polymer example. This is a example of graphene films. So, in the left side is a topography image. You see a change in the brightness contrast, no doubt, and that change in the brightness contrast telling the height difference from 0 to 2 nanometer. The brightest part is 2 nanometer height from the bottom part of the sample. So, that height difference is maximum 2 nanometer here. We could not see much difference, we could see there is a difference in the contrast, no doubt, but it what additional things we see in the phase image, that you see there is a clear cut contrast difference in the phase image here. In the phase image you see some region are very dark, some region are very dark. This darkest part is minus 39 degree change of phase shift, and the lightest part is minus 32 degree in the shift. So, and now if we notice this, the brightest part or less shift, that means minus 32 degree shift is occurring, that is due to buffer layer, that is a carbon buffer layer. Then another region which there is 3 different color, one is most brightest, one is most darkest, and another is bluish color. The color is given by the operator, any color one can choose. The brightness contrast difference will certainly change, but any color one can choose. There is no need of giving a blue color or any other color, but their contrast difference telling that there is three different phases exist in the sample that we cannot get from topography data, whether there is 3 different phases. Now, these 3 different phases due to what, that the operator or the users can analyze. In this particular cases, that the brightest part is due to buffer layer, where the phase shift is less, and the darkest part is the 2 layer graphene, bilayer graphene, and the less darker part is the 1 layer graphene. Now, as the phase shift is in the negative direction, that is due to attractive force. So, attractive force is maximum with 2 layer graphene, then with 1 layer graphene, then at minimum attractive force, or we can say it is a repulsive force with the buffer layer graphene. So, the sample is presenting how there is a 2 different phases exist in the sample, 1 layer graphene, 2 layer graphene, and the buffer layers, which cannot be which was not able to be confirmed from the topography image. Topography image will tell us height, and in this way this gives the importance of phase imaging in the AFM. If we look at the another examples here, so how the oscillation ratio of oscillation of amplitude play important role. In this particular cases, there are 2 different ratio was taken. That means these are very close set point amplitude and the free cantilever oscillation amplitude. That means it is a light tapping of the probe. Light tapping do not give much distinct contrast difference, but when the tapping is increases, medium tapping we could see the contrast difference of the 2 layer graphene and 1 layer graphene. So, this ratio of the set point amplitude to the free current level oscillation amplitude by changing, we can now here notice the 2 different phase in the sample. So, in case the light tapping do not work, do not produce enough contrast difference, then a hard tapping can be utilized to get the contrast difference or clear phase difference in the AFM image. As these are negative value suggest the tip motion in the attractive region. If we look at the these are about imaging, we have discussed about the AFM imaging, contact mode imaging, then non-contact mode imaging, then tapping mode imaging, then phase imaging, 4 different type of imaging. Most cases, as I have mentioned, that we operate AFM in tapping mode. All kind of samples can be studied by tapping mode, and always tapping mode topography is simultaneously collected with phase image. So, while collecting the topography image, the phase image is automatically get collected. So, that gives a idea about the inhomogeneity of the sample in case they are in the sample. Now, we have seen here that we could achieve atomic resolution in the contact mode, and also to an extent with certain type of sample, organic sample in a very well controlled environments in non-contact mode also we can get in the present day atomic force microscope. But if we compare, certainly the atomic resolution is much easier to get with the contact mode than non-contact mode, and certainly tapping mode also take the advantage of both contact mode and non-contact mode, giving the atomic resolution image. But now there are certain factors that play important role or can create artifacts, and the artifacts are created due to several factors that is pointed here. One is damage on the sample features, surface features. So artifact because especially in the contact mode we have more chance to damage the sample surface, and once we damage the sample surface, that is nothing but is not true surface of the sample, but that artifacts, and this is more with contact mode damage of the surface feature. And if the sample is hard, if you are also doing the tapping, and if there is a non-uniformity or there is a rough features, then also possibility of damaging the tip. When tip damage occurs, then the artifacts become more severe in the AFM imaging. In addition to that, tilt and drift of the scanner, tilt and tip of the scanner can occur because of different various reasons, vibration, thermal noise, other factors will also play important roles, and that can also, if there is a drift, you see a shifts in the shifts in the image position and giving a type of elongated structure, giving an elongated structure. So, this is due to also artifacts, not the true surface of the sample. Then we have a piezo element hysteresis. We have discussed that in STM. Piezo element hysteresis is nothing but the extension or contraction change of the piezo element is not proportional, linearly proportional to the wide range of the potential. As per the definition of the piezoelectric, or we use inverse piezoelectric effect, we apply the potential and see the deformation of the piezo elements. So, that deformation or change of the extension or dimension is not linear for a large range of voltage, it is only linear in certain range, and due to non-linearity of the dimension, the hysteresis comes. And then creep, that is also we have discussed, it is a time dependent phenomena. Once we apply the voltage, negative voltage, all of a sudden the piezo element will not retract or back. So, it is a time taking process, and that time delay produces the creep. Optical interference, because optical interference also occur between the laser light reflected from the back side of the cantilever, and also if there is a sample is smooth. If the light we are the laser light we want to get strike on the back side of the cantilever, and during reflection if the sample is smooth, some light goes away and again get reflected, that would create interference, and that can also be region of artifact. Asymmetric tip, double tip multiple tips that we have discussed much in the STM discussion. So, those are severe as soon as there is a damage or some, as here it is with the contact mode of operation. In a contact mode of operation, that type of chances is high, you damage the tip, and then all the features that you see on the sample is not the correct picture, but due to the artifacts. If there is a double tip, you see all single features appearing as a double features in the image. If you have multiple tips, the tips having multiple probe having multiple tips, such as like this, like 3 different features, and they would give you 3 different features or distortions in the image due to the artifacts. Then we have electronic noise, we use lock-in amplifier, we use voltage control, all kind of electronics is used to operate the machine. So, those electronic noise can also play into a role. Similarly, building vibration, this vibration, because the vibration supposed to be as less as possible. If we want to measure in the sub-angstrom range the resolution, then our noise level should be at least 10 times lower than the resolution we want to achieve. So, those vibration or noise should be as small as possible, at least 10 times smaller than the resolution we are expected to achieve with our measurement. If we talk about the noise a little bit more, there are 2 type of noise, primarily thermal noise, because of thermal due to temperature, thermal fluctuation happens to the cantilever, and that is a fundamental source of noise. And that noise we can write as like thermal noise can be write like del Z thermal Th is proportional to the Boltzmann constant Kb and T divided by K, spring constant. So, thermal noise is this, and as the temperature is increases, then the thermal noise will deflect more, this much of deflection will occur, and this will create a noise. For example, if our K value is around, if the K value is around 10 Newton per meter, then at room temperature this del Z thermal oscillation will be around 0.2 angstrom. It is quite huge, 0.2 angstrom is quite huge, because we are here in AFM we are going to measure sub angstrom level resolution, particle resolution. So, this type of noise is not accepted in the atomic force microscope, but that is the cases one has to reduce this thermal noise. And then we have also noise due to sensor displacement noise. It is a short noise of photons arriving on the photo detector in case of when the laser light is get reflected from the cantilever, and that also that is proportional also to the frequency. The experimentally measured noise density is just the addition of the thermal noise, and the linear increase of the noise density is the modulation of frequency. This sensor displacement noise can be written as like NF sensor. NF sensor is like something like root over of 2 and frequency of modulation, amplitude modulation, frequency of amplitude modulation, frequency of the cantilever modulation, sorry, and NZ sensor. This is the sensor. This noise is proportional to the frequency of the modulation, which is directly proportional. That will increase with as the frequency increases, and our thermal noise NFTH is equal to root over of K beta. This is Boltzmann constant, then temperature, then also frequency, the free oscillation, then we have pi q and then pi q K spring constant, amplitude square. So, these are the factors that that play important roles in making bringing this noise. So, as we increase the frequency, that as we can see that the noise is increasing. In addition to that, if we look at this formula, in the bottom part we have spring constant. So, in order to increase the force sensitivity, the spring constant value is supposed to be small. Spring constant value is supposed to be small. When spring constant value is supposed to be small, you see the noise is increasing. So, that is again another problem. So, in order to increase the force gradient sensitivity, we prepare a cantilever which has small k value, but here it is acting in opposite direction. So, these will play a role in the noises in the AFM. We have different way of measuring, like thermal noise in the static AFM, static mode of AFM operation. We have also dynamic mode of AFM operation, which amplitude modulation, frequency modulation. So, all kind of different measurement system have certain noise that depends on several factors. These are the mathematical equation how this noise comes to a particular type of AFM measurement system. More details of this derivation of this equation can be found in the books. So, I have just directly put this here for your knowledge, that what are the different factors that influence the noise in the AFM. Then another important thing is the resolution. Particularly resolution in AFM is two kind of resolution. One is lateral resolution. Resolution means what is the minimum separation between two objects that can be resolved or can be visualized as a two distinct objects. What is the minimum distance that we can visualize as a two distinct object. So, now in AFM, in all other kind of microscopy, we have seen trying to smaller size of the beam, less diffraction, etc. Here diffraction do not play important role. Here one important factor that play a role is the tip size. Smaller the tip size, smaller force we can put, and we can measure also through the atomic scale. But in addition to that, another factor plays important role here is the vertical resolution. Vertical resolution substantially will impact the lateral resolution. So, for example, here is the two vertical objects, and they are of equal height, and in these cases, now let us say this del z value, this del z value is, let us say, that means this height value is around, let us say it is 0.015 nanometer. Then the vertical resolution, that means lateral resolution become d is equal to 2 r del z. So, here r is the radius of tip radius, and del z is this. So, now as I said, del z is 0.015 nanometer. If tip radius is, if r is, tip radius is, let us say around 5 nanometer, then you will get this d value is approximately 0.7 nanometer. Now, you see when the lateral vertical resolution del z is 0.015 nanometer, then our lateral resolution is 0.7, quite large value, that means poor resolution. But again, now interestingly, as if the height of these two vertical objects, two spikes change, then again the formula will change to, in this case, d will be equal to root over of 2 r, then bracket root over of del z plus root over of del z plus del h. This will be the resolution, this will be the value of our d lateral resolution for this case. So, now you see here again, when the height difference changes, this d value will increase quite a lot. If let us say if del h is around 2 nanometer, then this d value will be around 4 point, it will be higher, much higher, it will be approximately 4.8 nanometer. This will be 4.8 nanometer. You see much larger variation in the resolution. The resolution become deteriorated or become poor when the height changes. So, the concluding point is here that for a rough sample, for a much rough sample where there is features are quite large difference in their height, we cannot get very high good lateral resolution. That is the point, that is the problem with atomic force microscope. Lateral resolution is concerned. So, atomic force microscope is therefore good for smooth sample, not for the sample which are very rough in nature. So, what we have seen in this lecture that phase imaging provides additional surface information that cannot be obtained from the topography data. So, this is one of the points, and second is that there are artifacts due to several reasons. One of these artifacts is primarily due to tip and contamination. Contamination, once the tip touches to the sample surface, then it takes away some of the sample material, and once it goes to another places, the effect of that contaminants will come into picture or come into the measurements of the force, etc., and thereby giving the incorrect data or image. And we have seen the two noise, particularly thermal noise and sensor displacement noise, affect the resolution to a great extent, and therefore, they should be reduced as much possible. In addition to that, our lateral resolution in AFM not only depends on the tip radius, lateral resolution not only depends on the tip radius, but also the vertical resolution. Moreover, we cannot make a very sharp tip to get the best resolution. Too sharp tip also will create problems, particularly it will damage the sample. Because it is in contact mode or in tapping mode, very sharp tip can damage the sample. That also has to be taken into account when the tip is formed. Nowadays, that AFM tip can be carbon nanotube have been used or demonstrated as an AFM tip with a very small tip size, which is quite robust in nature. But commercially or in regular day-to-day AFM measurements, we use either silicon nitride or silicon tip. Silicon's tip radius is normally 5 to 10 nanometer. On the other hand, silicon nitride is little larger radius of the tip, that is around 10 to 20 nanometers. So, those type of tips are used, but they are good enough to give us atomic resolution image in the atomic force microscope. So, this is about the phase imaging and artifacts, noise and resolution. More detailed information you can get from these books. Thank you.